So the plan for today is to build on what we were doing last time with the simple harmonic oscillator. And then we're going to move on to finishing our analysis of the simple harmonic oscillator, proving the various claims that we were making at the end of the previous lecture, and then we will move on to begin the theory of atoms, where we take our entire course basically and bring it around full cycle back to where we began with atomic theory and Empedocles and all of his ideas, and now we will be able to see how we can formally prove all of the various aspects of the atomic theory. Now, let's though first recap where we were with the harmonic oscillator so we can begin today's discussion. The harmonic oscillator, a very quick review of what we had gone through last time, has the following Hamiltonian, which was quadratic in both the momentum and the position. That inspired us to go to a system of natural units so we could better bring out this hidden underlying symmetry. We showed you how to carry out a dimensional analysis so that we could replace the constants h bar squared on m or the other combination m omega squared with the numerical value of 1 by working in a special system of units which has a certain unit energy and a certain unit length. We then solve these equations to determine what those units were. The unit length, which we called x naught, turned out to have this value, whereas the unit energy proved to be this very interesting, very nice and simple h bar times omega. We then delved deeply into the position momentum symmetry. We showed how the corresponding change in representation is affected by a specific operator, namely the Fourier transform operator. We then looked at the effects of this Fourier transform operator, which we had already derived earlier in the course, which is simply to give us different representations for the corresponding operators of position and momentum, either in position representation or in the momentum representation. By then looking at the Hamiltonian in each of these representations and realizing that it is the identical operation in both position and in momentum representation, of course, once we've moved to our natural units, we then realize that the bound states must satisfy this very tight constraint that they are their own Fourier transforms up to, of course, a possible normalization constant. Based on that information, we were then able to just guess, more or less out of thin air, the ground state of the harmonic oscillator as being minus e to the minus x squared over 2, a nice simple Gaussian. We showed that that works in the time-independent Schrödinger equation, and even were able to pull out the expected energy. Or to pull out the energy, which was 1/2 in our natural units, or 1/2 h bar omega in traditional units. We then worked to find new states, excited states above this ground state. And to do that, we defined operators which we knew would perform exactly the same operation, up to, of course, a constant, in either the position or momentum representation, so that we could then apply these operators repeatedly to our ground state to generate a whole sequence of states. That operator, we began with what we called the a hat operator, which was just x plus the derivative with respect to x. Its momentum space representation is identical except for some constant which doesn't affect the final results because we didn't really care about our normalization constants at the time. We tried applying this to the ground state to generate a new state, but unfortunately it just gave us back 0, which was useless to us. So we went back to the drawing board, tried again, found another operator which has the same representation in the momentum space, up to again a constant, where we now subtracted the derivative from the multiplication by x. This then was much more successful. When we applied that to the ground state, we got what looks to be perhaps a very good candidate for the first excited state, which has a nice node in the center, so we know it's the first excited state. I then claimed that this indeed does solve the time-independent Schrödinger equation with an energy value corresponding to 3/2. We then applied this operator yet again to that first excited state, generating another state which again must be its own Fourier transform. So it's a very good candidate state to be a bound state. It turns out to have this form as our guess. So I'm putting a question mark. It's a claim, and my claim was that this also satisfies the time-independent Schrödinger equation because it has two nodes. We know it must be the second excited state, so I'd labeled it phi sub 2, and my claim was that when you did that test, you would find an energy value of 3/2. So before we go on to today's analysis, I just wanted to point out something very interesting in terms of the sequence of energies that we are seeing. And if this pattern holds up, there's a very interesting comparison to the Bohr-Sommerfeld result. Remember, the Bohr-Sommerfeld result was that, in fact, the energy of the nth state should be nothing other than an integer times h bar omega, where these integers are really just the natural numbers. They start at 1 and then count upward. And the results that we seem to be finding, in fact, comport very well with the Bohr-Sommerfeld result. Notice we are finding energies, or will find energies, that are all increased by one natural unit, 1/2, 3/2, 5/2. Just like the Bohr-Sommerfeld result always goes up in units of our natural unit, which is h bar omega. And it counts, though, 1, 2, 3. You will notice that the Bohr-Sommerfeld result goes up in constant increments because, if you remember, back to the beginning of the course, through the correspondence principle, the energy spacing should just be h times nu, where nu is the orbital period or the natural frequency of the system. So it's natural that we expect spacings of h bar omega, and so it's not too surprising that we are actually finding this constant spacing, 1/2, 3/2, 5/2. The only somewhat surprising result is that our sequence starts at 1/2, and it's a little surprising because it's a little different from the Bohr-Sommerfeld result. But of course, remember, the Bohr-Sommerfeld result was just a semi-quantitative result. We didn't expect it to work out perfectly. So I think, in a sense, the fact that it gives us the integers, whereas reality is giving us the half integers, is really more a testimony to the power of the Bohr-Sommerfeld result rather than anything else. And it shows you the power of the Bohr-Sommerfeld analysis, but it also underscores the fact that we do need the type of formal analysis that we're carrying out now in order to really get the proper energies for the various states.